Hello guys, how y'all doing? Today we are going to be finally doing our long-awaited episode, which is assembly. I had to drink some water, I got dehydrated. Okay, so assembly. I'm going to try to teach you all of assembly in this one episode, so it might be long, but you're going to learn everything you need to know. Okay, and so now assembly, I created us a little sheet here for all definitions and all you need. This might look long, but don't forget, I have a lot of dead space. So in your sheet, this should fit. Okay. Now, I'm going to explain each one of these to the point where you're not going to even need to refer to it really, except for things that are like you don't need to memorize. Okay. And so, first, we're going to start with sections. Whenever you want to use your code, so this is my assembly code right here. Whenever I want to use my code, let's assume this is C++. So, assume I'm doing C++. In your C++, when I want to, let's say, print, you'll do cout, then you do variable, and then you end all, right? Now, in my variable, I will initialize it, and I'll do int variable equals 10, right? Now, in assembly, I also have to initialize the variable to be able to print it out, or do anything with it for that matter. I mean, even if I want to do variable plus plus, I still have to initialize the variable. And so in assembly, where do you initialize variables? In your section data. So in my section data here is where I initialize everything. So if I want x, so if I want variable to equal 0, like I did earlier, I'll do variable, which is the name. Then I'll do the size. That's the only difference from C++, is you have to determine the size. Now, the size I'm going to use is db0. Now, what is db? db holds, so in my sheet right here, I have it right, where is it? Jeez, I'm so blind. There it is. RDB. Sorry, DB. DB holds 8 bits. And then DW holds 16. DD holds 32, and so on. And you have all these. Now, how do you determine how much space it takes? So for an integer, so if I want to store an integer, the way I do it is I take these bits and I raise them to the 2. So this will be 2 to the n. That's the maximum number of integers I can store. And so here, if I go here and I do 2 to the n, 2 to the 8, sorry. You see, that's 256. So the maximum I can put in here is 256. If I put 257, this won't work because that's more than the storage it can hold, right? And so if I want to store even more, I will have to move up. And so going to my sheet back, DW, which holds 16. What's the maximum integer DW can hold? So we do this to the 16, and that will be 65,000. And so now if I do, ChatGPT be cooking me right now. Keeps coming in the way. DW. This will hold a maximum of 665, whatever it was, 536, 536. Now anything if I put 537, that'll be too much. Okay? And so that's how you initialize your variables integers. Okay? Now if I want to initialize strings, so let's say I want a message, or actually a name. How do I initialize this? What I will do is db, and I will do the name, which is, let's say, my name. Actually, I'm not going to put my name. I'm going to put Gravy, just because she's the #1 supporter, so I got to use her name. Okay, so like we said, so db, if we go back here, db is 8 bits. And so I have here 1, 2, 3, 4, 5 letters. How much does each letter take? And using ASCII, each letter, so you see in a string, each letter takes 8 bits. So each letter takes 1 dB, which is, 1 byte. And so here, the space I have 8 bits of space, and Gravy is 5 letters long, right? Each letter takes 8 bits. So I need 5 dBs to store Gravy, right? But the thing is, the assembler, as stupid as it is, it actually understands this, and it doesn't work this way. So I don't have to give it 5 dBs. What it does is it goes, okay, gravy is an array. Therefore, when you say dB here, it gives each index a dB space. So gravy has 5 indices, right? G is 1 index, R is 1 index, A is 1 index, V is 1 index, and Y is 1 index. In memory, each index has 8 bits. So if I change this to DW, actually, each index takes up a space of, so DW takes a space of 16 bits. So even though I only need 8 per letter, I'm using 16. And so actually, when you store a variable, all you do is this, dB, and this will automatically assume, each letter is 8 bits. And so each element is going to take 1 dB. So this is 1 dB, this is 1 dB, shit. The R is 1 dB, A is 1 dB, V is 1 dB. Okay? It's not the whole thing is 1 dB. Each letter takes 1 dB. All right? And so that's how you initialize your strings, and that's how you initialize your integers. And you initialize them in your section data. All right? Now, let's say I am taking input. When I initialize it like this, well, this is variable that doesn't have anything. You can't do this in your data. You can't have an empty variable in your data. Your data always has to have some variable. The variable always has to have some value. But if I'm taking input, I don't know the value until the user inputs it. And so what do, there's a section called a .bss. In this section, you put this stuff, you reserve memory. Okay? So how do I reserve? So let's say I'm taking name as input. Okay, so how do I take this? So what I do, I go section.bss, and I'm like, okay, so I have a variable name. I don't know how long the user is going to put. Maybe their name is 5 letters, maybe it's 10, maybe it's 20. Let's say it's a maximum of 100 letters. How do I reserve 100 letters? So the syntax here, if you see section.bss, res_b takes 8 bits, which is aka 1 byte. And so if I do the name, right? So here you put the name of whatever you want to reserve. I could put name, I could do last name, like this is anything you want. I'm just using name for the convention. Okay. And so name is what I'm trying to store. I don't know how long. So what I'm going to reserve B. Now each number of reserves. So you see up here, actually I put reservation call. So you do reserve B. And then after you put the reservation size. And so here, if I put 1, what can I store with 1 res_b? 1 res_b is 8 bits. And obviously, we know each letter takes 8 bits. So if I'm reserving only 1 res_b, I can only store 1 letter. Only makes sense. So if I reserve 5 sections, then I can store 5 letters. All right. So now the other thing is, if I go here, there's other things. So if I do res_w, then that's 16. So if I do here res_w and I take only one of it, res_w, I take only one of it, how many letters can I store here? Well, res_w, so you see as if we go here, res_w, number of words, and each res_w is 16. And so we know each letter is A. Therefore, in one res_w, I can store 2 letters. Okay, so this stores 2 letters. So what if I want to say the longest name someone can input me is 100 letters long? Now, I mean, nobody's name is 100 letters long, so I should be safe, right? So I'll do is res_b 100. Because we know each one res_b is 1 letter. So 100 res_b's is 100 letters. Or you can also do this if you want to do extra math. You could do res_d, so that's 32. So each res_d holds 4 letters, or each res_q holds 8. Now 8 times 10, if I do res_q and I hold 10, I know each res_q is 8 bits. 8 bytes. Each byte is 1 letter. And so each one holds 8. I have 10 of them. 8 times 10. This holds 80 letters. Okay? And so that's really how you reserve. And this is the same thing for integers. If you want to reserve integers, if you do resb, that's 8 bits. And so we do 2 to the 8. That's 256. So if I want to do an integer here, I'll do number, resb. And if I do 1, this holds 256 integers max. If I do 2, this will be 512. If I do 3, this will be, I believe what 512 plus 200 is like 700 some shit. You get the point. All right, so that's how you reserve area, and it's in your section .bss. All right, now so we spoke how to initialize variables. We spoke about how to reserve space. Now, how can you write your code to do stuff? And that will be in my section .text. In my section .text, under here, you do global start. And what this means is when the compiler first runs and compiles, your assembler assembles your code, it looks for your start section. Okay, and so first I declare this. I'll be like, okay, there's this start section, and here is the start. And so this is the equivalent. These two, so these two, all right, are equivalent to your int main in C++. This is like I'm doing int main. I'm telling my assembler this is the start. All right, so you'll always do this. This will always be there. Okay, and so under here is what you'll do or your operations. So let's say you want to compare, you want to move, you want to add, subtract, you want to loop, everything, if statements, all goes here. Okay, so now going back here, let's recap. Data is defined, is data defined before compilation, or initialization of variables, let's say. This is where you initialize your variables. Okay, in your .text is the actual code and executables instructions, and .bss is to allocate space for future use. Okay, so now that we have accomplished this, we're gonna go over our first activity from Assembly Language Programming 1, and this tells us a couple things. Write assembly declarations for the following variables, putting them in the correct sections of your program. So a single sized integer. So we want an integer that is 20, named age. So actually, before we choose the section, we know it's going to be called age, and we know it's going to hold 20. Now 20 is how long? 20 can be fit within 8 bits, right? Because 8 bits fit 256. 20 is less than 256, so I can fit in 8 bits. Now if I go back to my thing, 8 bits is a dB, right? So you see if I go here, dB is 8 bit. And so this is going to be dB long. Now what I just do, I just initialize the variable. I did age, and I gave it a value, 20. And so this goes in my section data. Okay? And now after this, what does it want? A double-sized integer containing 1,000,000. So since it says double, you can already guess here this is a double word. So you could do DD for size. But if you actually want to do it more, how do you say it? Mathematically. So if you're writing your own code and you don't know whether to use a double, what you'll do is, okay, so this is what? 1. This is 1, 2, 3, 4, 5. Actually, why am I counting like this? This is 1,000, million, billion. So this is 1 billion. Now, can I fit 1 billion in 2 to the 16? So in 16 bits, can I fit that? No, that's 1,000. Can I fit it in 32? What is that? So that's million. Oh, sorry, 1,000, million, billion. But this is 4 billion. I'm only trying to store 1 billion. So can 1 billion be stored in a 32 bits? Yes. And so now what I can do is store it. And so what it says is named large. So I'm going to name it large. What's the size? The size is, we said 32. So if I go here, which one's 32? DD is 32. And so DD. And what else here? We put our number, which is 1, 2, 3, 1, 2, 3, 1, 2, 3. That's it. I initialize it. And so here it says a list of grades containing 99, 100, 86, and 40. And we haven't spoken about lists yet. And in here, I do have a list. So you put the name first. So let's put the name. The name they want is named grades. So the name we want is grades. Then it says in my here, it says the next thing is the size. So whether it's DQ, DB, or DD. All right. Now what's the size? How do you determine the size? For a list, it's just like when we were initializing when we were initializing a string, we only declared the size of one element, and that applied this size to each element. So here for this list, remember a string is a list, and so since we're trying to create a list, our grades is the same thing. What I'm going to do is I'm going to give it the size I want each element to hold. Now I see these 5 elements, all of them are below 256. So all of them can be fit within a DB, because DB is 8 bits, right? And it fits 256. So DB, and then what I'll do is 99, 100, 86, 40, 34. And now each section can hold a maximum of 256. If I do 257, it's wrong. So if I do 256 here, if I do 256 here, that's fine. Each element is a size DB. That's how you read it. All right? And so back to what it was. That's done. Now a string constraining hello named str. So again, str, what's the size of hello world? This holds 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Pay attention, I also counted the space. All right? So this is 11 letters long. So what I can do is db. Now remember, we said for string is the same as grades. Unlike age, where you do some calculations, each db holds one. So see here, each db is 8 bits, and each letter is 8 bits. So I can just do this and do hello world. Right? This works because now each section holds 1 dB, and one letter only takes 1 dB, so this is enough. Right? And so this is 1 dB, this is 2 dBs, 3 dBs, 4 dBs, 5 dBs, and so on. All right? Now at the end, there's something, there's 10, and there's 0. Now in here, I did put it, 0 is the null terminator, and 10 is backspace. And so the reason I put 0 here is to tell the assembler that once you're reading all these one by one, right, as you're reading this, when you encounter the 0, you're done. The string is done. If I don't put this here, it won't know where the end is. It'll just keep going into memory that's not even there, and it'll crash. It'll be segmentation fault. And so when I put 0, I tell my assembler, hey, like you've reached the end. Okay? When I put 10, I'm telling it, okay, now there's a new line. And so what's the count of this? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right? And even if I had my 0, this would be 12, because this does count as 1. Oh, okay. Now, next one is a placeholder for a byte size name. Now, since this is a placeholder, what the trying to tell us is just reserve. I don't have anything to put in there. I just need the space. And so when we reserve, we know it's in the BSS. Now, they want a placeholder named small, and they want it for a byte-sized number. So 1 byte. That's all I need. Resb 1. And so that's a 1 byte. Remember, if I go here, Resb is 1 byte. And so now I'm taking space of single byte. Right? A byte. All right. Now second section is a placeholder for a list of 5 grades. And so first we're going to name them final grades, right? And now I got to reserve space. Now obviously we have a placeholder for a list of, we have 5 grades, so we have to reserve 5 spaces, and it's a single integer. So since it's a single, then that means it can fit within a Resb, right? A single integer is less than 257. It's a single, so it's 0, 1, 2, 3, single. So that can fit within an 8-bit because 2 to the 8 fits a maximum of 256. Okay? And so res B, now if I do 1, this can only fit, this is not a list, this can only fit a single, integer. So I want to reserve 5 of these. And so that's how I do it, a list of 5 grades. Now let's confirm our answer. HDQ 20. Large do, so he did do, which is way bigger than DD, but this is right. This still fits within a DD. Great DQ. 99. He used bigger, again, bigger memory. This still works. DD, right? He just used way bigger memory. So now each section takes 1 DQ. STRDB, hello, and then ends with the null terminator. And then section, we have a small res B1. And we have a final grades res Q. Again, he used a bigger one, a res Q. I use a single res B with 5 sections. So that's the difference. All right, so activity 1 is complete. Now we're gonna go into activity number 2, which is promoting. This is using printf statements and other things as such. Now deleting this, and we're gonna go back here. This is where we're gonna go into syscalls. Obviously, we're gonna use our section.text, since now we're doing some functionality like we're writing, we're printing, we're scanning, etc. Now this might look intimidating, but it's actually pretty simple. Okay. So first, obviously, we're gonna what does it want? Prompt the user to enter their name. So first, we're taking an input of name. Do we know how long the name is? No. Therefore, we have to make a section.bss and reserve some space for this name. So this name is going to be how long? Let's say RSB 100. We're going to assume the name is going to be 100 letters long, and we're going to just save that. Okay? So we're going to reserve 100 spaces or 100 letters. And then here, you see it says reserve 100 characters, which we did. And then it says print, what is your name? Now we haven't learned how to print yet, but the first thing we know is any functionality goes in our .text. And like we said, we have to do the int main, so global start, and then we have to do start. Okay, so this is our int main. Now we do functionality. Now there's 2 ways. You can either do a printf, or you can use something called a syscall. All right, so you can either use a syscall, which is syswrite, or you can use a printf. Now I'm going to teach you both. Printf is easier to use than syswrite, but just in case you need to know this, he did mention it, so I'm going to teach it. It's pretty easy, it's not too hard, and it's in the this table, so it should be fine. Now in order for me to use a syswrite, well, first I have to make a syscall. So syscall, right? This is standard. If you want to make any system call, you do syscall. Now how do you identify which syscall you want to call? There's syswrite, there's also sysread, there's sysopen, there's sysclose. Now all these are system calls. Do you need to know them? No. The only ones you need to know is syswrite for now. Okay. Now how does the assembler identify that this is a syswrite or a sysread or a sys whatever? The way it identifies it is checking these registers. Okay, so if I want to call a syswrite, the RAX register has to have the value 1. Okay, if RAX has 1, you're doing a syswrite. Okay, so I want a syswrite. So I'm going to do move RAX 1. I am moving number 1 into RAX register. That tells the assembler I'm using now a syswrite. Okay, now what's the next step? The next step is in my RDI, if I want to do output, so if I want to write to the terminal, then I will do 1. So I will put 1 into my RDI. That's me saying I want to do a standard output, which is I want to output to terminal. Okay, so this means output to terminal. Okay, and so if I put in my RDI 1, my assembler will be like, oh, okay, that means I output to terminal. Now if I put 0, that means I input from terminal. Okay, so if I put 0 in my RDI, the assembler will be like, oh, like somebody's gonna give me input. But if I put 1, it's gonna be like, oh, I'm printing something to the terminal. And so since I wanna here print, right, I wanna print, what I'll do here is move RDI, and remember, printing is 1 in my RDI. So in my RDI, I'll put 1. Now, what's the next step? The next step is I have now RSI register. What's the RSI register? It's the location of string to write. Okay, so you see location of string to write. So what's the string I want to write? Well, I haven't declared that yet. It's a variable. And so 6 section dot data. And now what do I want to write? Let's say this is the message I want to write. Now the message I want to write is, what is your name? Remember, if we want to declare a message, we just do db, and then we write what we want, which is what is your name? Okay, and then we do a null. Or I'll do a new space, which is, that's what I'm doing right here. That's 10. Okay, 10 means new line. All right. And so now, if I want to print, right? So if I go back to my table, if I want to, so in the RSI, it takes the location of string to write. So let me put that in. So move into my RSI, my message, which is, so this is the address of the string I want to write. Okay. Now what's the next step? In the RDX, put the length of the string. So in the RDX, put the length. What's the length? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, plus this, so 18, 19. All right. All right. So now if we run this, if I run this right here, you see I get an error. Now, this is, oops. If I run this right now, it works just fine. But you see, it completes with an exit code -11. Now, how do you, so in assembly, when you create your code, in your C++, you have int main. And then when the code runs through the int main and it gets to the end, it's like, okay, I'm done. And it return, you do like, you do return 0. Now in assembly, you got to do the same thing, which is called a sys exit. Now for a sys exit, where is it? Whoops. Okay. So for a sys exit, I got to put in my rack 60. I got to put in my RDI usually 0. That's my error code. So I want to return, return 0, return 1. I want to return 0. And so in my RAX, so you see now I do all this stuff. This will print my what is your name. Then what I'll do is a move rax 60, because I want to return 0, and I do move RDI 0, and then I'll do syscall. Right now this syscall, we'll see, in my rax there's 60, in my RDI there's 0. This is a sys exit. And see, when I run it now, I get code 0. See, if I change this to 50, 59, and I run it, I get 59. This just tells the assembler, hey, we've reached the end, you're done, return 0. Okay. And so now this is us doing this part using my syswrite. Okay. Now how do I use it? How do I do it using printf? Okay, so now you guys understood how to use a syscall. I'm gonna delete this and start again. Actually, I'm not gonna start again to save time. I'll just start my actual code. So to use printf, printf is not actually a function of your assembler. So I can't just do, you see, if I do here like printf, and I do like message or whatever, like you think that you could do with this, like the syntax for it is not even the same. This is for C language, but the prof is, so there is a way for you to link it in your assembly and use a C language within your assembler, but on this website that's not possible, and so we can't really test it, but I'll teach you how to use it. Okay. And so now how do we, so now we're gonna actually write this exact function. And so now we want to do printf. First, go to your table, printf. In my racks, I gotta put, so you see it's a floating point. If you're passing a decimal, set to 1, else set to 0. Now in my print, it's a string. It's not a floating number. It's not a decimal point. And so in my racks, I'll just put 0. So move racks 0. Okay. Now, what's the next step? The next step is in my RDI, the format address or string. Now, I don't have a format address, and we'll talk about the format address. We just have a string. So let's pass this string to RDI. Text format to be printed. All right. Well, we don't have format, so ignore this. We're just going to put string into my RDI. And so I go here. I'll do move RDI. And I'm going to put my message into it. That's the string I want to print. Right. Now, what is the next step? The next step is these are for placeholders. But again, this is just a string. We don't have placeholders. So we're not going to use this line. We're going to ignore it for now. We'll get back to it in a bit. Now, one thing is in assembly, whenever you call, so the way I'm going to call printf, this is how I do it. Whenever I call a function, whether it's printf or any function or a function I made, any function, whenever you call it, there's something called a stack. Okay, if I go back here, there's something called a stack, which it holds, you know, all my little functions. This is the stack, and it holds, let's say, whatever variables I have. Okay, and so this is my, you can think about it as my RAM. All right. Now, whenever you call a function, your RAM has to be multiple of 8 bits. Oh, sorry, 16 bits. This is a must. Okay. So if I only had 8 bits here, then I have to add one more 8. Okay. This is a must. It's just like there is a reason for it. But for now, just know this is that every time you want to call any function, whether it's a scan or whether it's a print or a scan, then you need to have a multiple of 16 in your RAM. So each line takes 8 bits. This is 8, and this is 8. That's 16. That means our stack is aligned. Now when I call my printf, it's fine. The stack is aligned, so I don't gotta align it. It's already a multiple of 16 bits. 8 plus 8 is 16. That's a 16 divided by 16 is 1. That's a multiple of 16. So I don't align it, and I can just call printf. Okay? Now, if you're wondering why do I need to have the stack a multiple of 16, is because when they first made CPUs, they did some architecture. So here we're using x86_64 architecture. For this architecture, when they first made it, they said the stack has to be a multiple of 16 before you call any function. So every time you call a function, the stack has to be a multiple of 16, and that's just the way it is. And so now, here, when by the way, this is just because it's hardware built that way, so you just have to do it. There's no specific reason. If you want to actually understand the reason, you'll have to understand the way it's built, and it's something to do with easier way to send data to the cache. You don't need to know this, but just know before you call a function, make sure you have a multiple of 16. So this is 8, that's 8, that's 16. That's done. Okay. So if I had like something else like move RDI1, or sorry, let's use like RCX2. Now this is 8, 16, 24. That's not a multiple of 16. So what I'll do, I'll just push RBX, and then under here I'll pop RBX. Why do I do this? Now this is 8, 16, 24, 32. You see this line adds 8 bits to the stack. Okay? You see I push RBX to the stack. RBX is 8 bits big. And so now it becomes 32, which is a multiple of 16. So then I can call the function, and then after it, I just remove it, because like, that's it, I'm done. Right? Like, I don't need to align anymore. And so for here, we do printf, but I believe the prof push, he does push RBX and pull RBX before and after a call every time, regardless if it's a multiple or not. I don't know why he does this. My friend is asking him today, so I'll let you guys know maybe on the YouTube channel like what the answer is. But to my understanding is that you only do the push RBX when it's not when it's not aligned. But here it's aligned, we're not going to push anything. All right. And so now, obviously, I did my rack 0. I put my RDI message. I did call printf. This will do this line. Okay. Now, what I want to do is I want to grab name. In order to grab name, I use scanf. This is for input. So how do I use scanf? I go back here and scanf. In the RAX, set to 0. Why? What is the RAX? When I do scanf, if I'm taking, let's say, 10 inputs, it returns me how many items were matched. So if I'm taking 10 and a person put 10 inputs, then that's 10 matches. And if I check my RAX and it has 10, then I know people input the amount I want. And so what I do, I always set it to 0. So let's say before, so you see right here, I set my RX to 0, but what if I set it here to 1? And I'm trying to do an input. When it returns me how many items were matched, it's not going to be the same amount 10. It's going to be 11. Because the initial is not 0, it's 1. So I'm going to be off by 1. And so that's not good. And so that's why we always set our RAX to 0. And so here, so what I'll do is move RAX 0. So return this to how it was. So now just to confirm, make sure my RAX is 0. I'm going to put 0. And then what's the next step? RDI. Put the format address, how the string looks when you take the input. Now that means I need a format. So format db. And we didn't talk about this. This is going to be my placeholder. What do I want in here? I want s, which is the name, right? And I'll do -0. So I just declared a string of size db. Okay, so this is the format. This is how I want it to look like. I want this to have gravy. That's what I wanted. So my -s is where my gravy will go. Okay, and so in my table, it says put your format, the format address, into my RDI. So I'm going to go here, move RDI, and I'm going to put into it my format. Okay, now what's the next step? The next step says your RSI, RDX, RCX, R10, R8 are the first inputs. So what does that mean? If I want to take one input, right, that will go in my first, which is RSI. So RSI is my input. Now, where do I want to take this input in? Obviously, it's going to be the name. So RSI, when I do my scanf, the first input will be returned to RSI. Okay? And so where do I want my RSI? So I'm going to put my name. I'm going to put the space I reserved into RSI. So now RSI is this space. Okay? So now when I call the scanf and it takes the first input, it will put it into the space that I reserved. Okay? Because this RSI is the reservation space. The reserved space. I don't know why I said reservation. Okay? And so when we go here, my RSI is the first input. Let's say I want to take two inputs. Let's say my format was this is the first input, and this is the second format. So you see, I take two inputs. So what I'll do is move. What's my second input? RDX. So RDX, and I'll take my second input. Obviously, I gotta reserve. Let's say like last name, let's be 100 letters. So let's say now we take a last name, and this is gonna be last name. Okay. And now what this means is when I do call scanf, this, so here it's gonna ask me for name and last name. So I'm gonna say, you know, gravy fries. Okay. And so gravy will now go into RSI, and since RSI is the name, gravy goes here. Then fries, my second input, you see it's separated by space. If I remove this space, then I have to put this like that. Okay, and so it's separated by space, and so fries will get collected and will be put into RDX, which is my second argument, and then my RDX is the last name, so it will be fries will go into here. Okay, and so now obviously we don't need this, we don't need this, right? And now so far, if we recap our code, first we're gonna print this message. In order to print the message, we need racks to be 0. because 1 means we're passing float and we're not passing numbers, so that's 0. RDI needs to hold the message we want to print, and then we're going to call it. And before we call it, this has to be a 16 multiple, which 8 plus 8 is 16, 16 multiple. Okay, so that's done. Now next step, the move racks is 0. So here I want to input my name. And so what I'll do is, okay, in RAX, this will tell me how many inputs I'm taking. So I'm going to initialize 0. So after I do the call, this should be 1 because I'm taking 1 input. And why is this useful? It's so I know how many inputs I took. So after this runs, I know this will turn to 1. So I know, okay? If I set it to 0, then at the end of this, I'll get 2, which is off by 1. So you always want to set it to 0. Then the format of what I'm taking, so my format is going to be only one name. So it's just going to be like this. And so here S is for string, D is for number, C is for like a single character. And so here S for string. That's the format. And then in the RSI, we want to put, where do we want to put this input? Like in what space? And this is the reserved space, so we're going to put it in here. Then we call it. But before we call it, this is calling a function, needs to be a multiple of 16. So 8, 16, 24, 32, 40, 48. Now 48 divided by 16 is 3. Therefore, this is a multiple. And so I'm going to leave it as is. I'm not going to push my RBX because this is aligned. All right. Now after this, what do I want? I want to print welcome with the name. And so obviously I have to have a string. And so let's do that. I have to have a format. And so we're going to say this is welcome. Actually, we'll just name it str for string. Okay, this is going to take something like db. And it's going to say welcome. And obviously my s. And I put 0 for end of line. Even here, I'll put 0 for end of line. Okay. Well, sorry, null terminator. So like, yeah, end of string. All right. Now, how do I use this? I want to print. How do I print? Go back to my table, which is print. In my RAX, it takes a float. I'm not passing a number. I'm passing a string. So this will be 0. All right. So move RAX 0. Now, before you move, you always want to check if in the above steps you need the value of RAX. I don't. So therefore, I'm fine with this statement. Okay. Now, what is my second? RDI takes the format address string. And so my RDI takes the format address. So move RDI. What's my format address? str. Okay. Now after this, okay, what is my next step? RSI. RSI takes the placeholder. So you see my placeholder is -s. In my RSI, I will put the first placeholder. So if I do here move RSI, what do I want to go instead of this s? The name. And so name. But this is the address. What I want to take is I want the actual name. And so I dereference it. Right? Now the name gravy goes into the RSI and not the reference, which is the address. Okay? And so what I'm trying to accomplish here is if I would to have another integer d, then what I'll do is in the next one, I use up my RSI for the name. The next one will be the RDX. And so the second input, see, first is S, second is D. And so I will do move RDI. And I put, let's say, oh, sorry, not RDI. What is it? RDX. I'll put, let's say 10. Now 10 will go into here. Okay? And so this is how you do multiple inputs. And so now that we got our input, RSI, the placeholder, what's going instead of our -s. And you see, I did say here, pass string and not address. So we pass string and not, if you just do name, that's address. If you do in brackets, that's name, that's the value at that address. All right. And so now I can call printf, right? And so now before I gotta align. So we have 8, 16, 24, 32, 40, 48, 56, 64, 72, and then 70, so it'd be 80, I believe 80 is a multiple of 16 by 5 or 4. 80 divided by 16, it's 5, yeah. So you see, now that's a multiple of 16. So all I gotta do is call printf. Right? Now, if by chance this wasn't aligned, so you know how I counted and it was a multiple of 16? If it wasn't, what I'll do is push RBX. This will, right? So this will, if this was off by 1 8-bit, this will add that extra 8-bit. And then after I'm done, I'll pop it because I don't need it. I'm just doing it as a filler, right? Just so I have it aligned. That's it. But here, it's already aligned. I don't need to do this. Okay? So now, going down to his example, he has his data. He has a prompt. What is your name? Which we have. Our message. He has a format. And that's going to be the name format. And this is the message we want to print, which is our string. Okay? Now in the BS, he reserved 100, which is also what we did. And then now here, he moved RDI prompt, which we did. And then Rax took 0, but he pushed. So you see, he pushed. Even though this is aligned, this is a multiple of 16. 8 and 8 is 16. I don't know why he pushes every time. Maybe he's just trying to tell you guys to always push. I don't know what he's trying to do here. The correct way is that you don't push if it's not a multiple. Sorry, you don't push if it is a multiple. And so, anyways, you guys can check the rest of it. It is the same. And so that activity is done. Now we're going to go into activity. What is this? Multiplication. Okay. So multiplication is actually pretty simple. It's one of the simplest things. So here it says, write a language code to multiply numbers 10 and 6 and indicate the result values of the registers after multiplication. So first thing, right, we do text, and then obviously we got to do global start, and then we do start, and then now we want to multiply. Dude, I did not leave anything out here for you guys. Everything you need is here. See? Multiply. Now when you do multiply, you multiply the register, and the register, you see when you add, I add register A plus B. Okay? It makes sense. And you see right here I said A plus B equals A. Now for multiplying is not the same. You only pass it one register, and the mul, this mul function operation, by default, it assumes that you're multiplying it by the RAX. So if I do mul the register, it will take whatever this register is, multiply it by the RAX, and then the result will be stored in the RAX. Okay? And so now if I want to multiply 10 and 6, what I'll do is I'll move 1 into RAX, and then I'm going to move another one, let's say RDX. I'm going to, actually, usually here I put them in order. So you see RAX, RDI is the one you usually want to use after. So let's use RDI. And I'll put in my RDI 6. And now I want to multiply. So I'll do mul RDI. Now what this will do is it will take RDI, multiply it by RAX, which is 10 times 6 is 60. Then it will place the results in the RAX. Okay? And so that's really about it. Now here, there's also, where is it? For the mul. You see in the mul, this is a regular, sorry, not regular, this is a register, but here it's unsigned. So if I'm doing -6, if I'm doing -6, instead of mul, I will have to do I mul. And this will take care of my -6, so I get -60 at the end. And you see, I also put it here. If you have a signed number, you use I mul. And if you use an unsigned, you just use mul. Now, can I use I mul for an unsigned? Possibly, but it's better to keep it using this convention. Okay? And see now, RDX holds int that don't fit in RAX. This is a little thing that you have to do. And so you see here, this technically does work. But my multiplier, remember how I said it returns it into RAX? So after this runs, RAX equals 60. The register RAX equals 60. But there's also something called RDX. So RDX equals 0. This you'll always have to do. Now why? Because if my multiplication, so my RAX hold, I believe, 32 bits. Okay? It holds 32 bits. Now 32 bits, root to the 32, is 4 billion. Okay? This is how much it holds. Now, if I do a big number times a very big number, the result I get is more than 32 bits. So what this function will do, it will store the first 32 bits in my RAX, and then it will store the rest of it, whatever is left, into my RDX. But if I don't do this step, and my RDX was previously 50, my number is going to be wrong. Because it's going to, the rest, so whatever is left over, is going to be stored in here, but this is 50. So it's going to be like whatever is left over plus 50, which is wrong. So I'm going to set it to 0 to say that if there's any leftovers, this is initialized. It's 0. You can store things in and it'll be right. Right? Like the information in here, like if it's 50, I'll be off. Okay, so I hope that makes sense. All right, so that's why you'll see him in lectures. So even here, you see what he did? He did RDX 0. This is in case my number is too big. Okay, and then he did RDX 10. He did RCX 6. So same here. Let's remove this. Mul RDI. And you see he used RCX for R6. We use RDI. It's the same thing. Let me fix this back to how it was. All right, and then you see RDX should be 0 because we don't have any leftovers. 10 times 6 is 60. You can fit 60 in the RAX, so that's fine. Therefore, my RDX will stay 0. And then my RAX should be 60, which is the result. All right, and as you can see, I wrote it here. MUL, the result is RAX equals. So we'll do the multiplication, and then it will equal it to the RAX. Your division, same exact concept. All right, and so this is done. Now we are going to go into if statements and while true loops and stuff like that. I'm going to take a quick break and I'll be right back. Alrighty, so we're back, and now we are going to do if statements and how you do them. Okay, so first we're just going to initialize the 3 variables they want us to initialize. Okay, so here they initialize 3 variables. Let's initialize. We know when we initialize in our data, and we know x has a size of 1. The reason it's dB is because I can fit 1 in 8 bits. And therefore, this is going to stay the same. And then obviously my y also can fit. 2 can fit in 8 bits. And my z can fit into 3 can fit into 8 bits as well. So I'm going to keep it like this. If this was a bigger number, like 300, this will not be dB. This will be, I believe, what, dW? You see right here? Yeah, dW, which is 16, which is the next biggest size. Okay, but obviously this is only 3. So it fits in a dB. All right, now after we do this, we have our section text and we have our global start, and then we have our start. My mama just walked in and gave me bomb food, bro. Jeez. All right, back to coding. So now we start. Now at the start, what do we want to do? We want to compare. We want to do if x is less than or equal to 5, do this. So first, let's do this operation. Okay, so how do we do this operation? Obviously we want to add x plus y. Now I cannot, this is, remember I said this is your RAM. I cannot in my CPU access my RAM. I can only access my RAM from my register. And so what I'll do is move into my racks, let's say. I'm not gonna actually use racks because racks is very common for other functionalities. Here I'm doing a print, and so I don't want to mess with my racks. I'm gonna use something that's more later on. And let's see, up here is I have it all. So racks, RDI, RSI, RDX. I'm gonna use an R10. This is just another register. It's a general purpose register. So I can use R10, but actually, let's see. My printf uses racks, uses an RDI, and uses an RSI. So RDX is empty. Now I'm only taking 1 input, so I'm only using RSI. If I'm taking 2 inputs, I will use, RCI and RDX. But so since I'm using RSI only, RDX, RCX, R10, R8 is not going to be used. So I'm going to use RDX since it's just the first up there. So I'm going to move RDX. I'm going to move into RDX. My X, right? 'Cause I'm trying to do these operations. And so first up here, I'm going to list them. because I'm going to do something, right? Here I'm going to add x plus y. Here I'm going to add x plus z. So obviously I got to access these. And if they're in my RAM, I can't access them. So I'm going to bring them into my code. And so what I'm going to do here, I'm going to say rdx equals my x. And I want only the variable. I don't want the address. I want the variable. And so here, I'm going to also do rd. So what is after rdx? I have rcx and I have r10. So rcx, which is going to hold my y, and move r10, let's say. Actually, I'm going to use a. And then I'm going to put that as z. Okay, so now each one of these registers will hold 3, 2, 1. Okay, now that this is done, what I want to compare is x less than or equals to 5. So how do I compare this? Then I can do CMP. CMP is compare, and I have it here as well. CMP A and B takes any two values or registers. So I can either give it two registers, or I can give it two values, or I can give it a register and a value. And so I compare two things. And so CMP, and what am I going to compare? I'm going to compare my x, which is in the RDX, and I'm going to compare 5, which is just 5. Right? It's not in my RAM. I don't have to grab it or do anything. I can just say 5. All right. Now, can I do this? Yes. Is it less efficient? Yes. I don't need to do this and move and do all that. I can just do this. Now, since I compare, when you compare, the way comparisons work, let's see if I wrote it here. The way comparisons work is when it compares two things, it will set these flags. Now, it's good to know these flags. Are we going to use them? No. Is it good to know them? Yes. And so, how does it work? When it compares two things, it will set these flags. Okay? And then when I use these jump symbols, they check these flags and they act accordingly. All right? And so when I do this, assuming my x is more than 5, this will set some flags. Do I need to know them? No. What I do need to know though is if, obviously my statement is if x is less than or equals to 5, so which one catches this? Now you see here, GBE, so this is unsigned. Signed is for negative, unsigned is for positive. My numbers are positive, so it's unsigned. Okay, and then I want to use GBE. So what GBE does, this will check the flags that would occur if my x is less than 5, right? And so when I do this, GBE, this will check this. If A is less than or equals to B. If A is equals or less than to B, then what do I want to do? I want to jump to a section in the code, right? I want to do this, okay? So I can either do jump to, let's say, x, y addition, and then I'll define it here, right? And I'll do the addition here. Or I can do it another way. Now, the problem with this is here. Watch this. Now, pay attention to this part. This part is very important, and people will get it wrong. Here, this will jump when A less than or equal to B. Now, my x is 1. My B is 5. That means this will always work. Every time this runs, every time this condition runs, my x will always be less than or equals to 5. Okay? And so what I'm going to say is I'm going to switch this. I'm going to check, instead of doing this, I'm going to say, well, actually, you know what? For this specific one, you can do it both ways, but for while true loops is very sensitive. For this one, you can do it both ways. So here, I'm saying if x is less than or equal to 5, jump to xy addition. And here, let me do the addition. So what I'll do is I'll do add rdx, which is x, and then I'm going to give it y, which is rcx. Now, if I go here and I look at my add function, a equals a plus b. And so my a is rdx. So my solution, so after I do the addition of x plus y, which is 3, that will get stored in my a, which is the rdx. So here, rdx equals answer. Okay, it's the first one. That's usually how it is. All right. And so Now, what happens is my code now jumped here and it finished this. It wants to go below. But obviously, there's nothing to go below 2. And so now I can say, well, if this works, you do the addition, then what do I want? I want to print, right? Because my else doesn't run. My condition is true. This ran. This gets skipped. This runs. And so let me do my print. And so here I can name this print. And here's where I do my print. Now in my print, what can I do? Let's see. And I'll explain, by the way, what these are. These are called labels. And I'll explain in a bit what they are. They're very easy to understand. And so I want to print. So I'm going to go up to my print. I need my RAX to be a float. Am I passing a float? No, these numbers are whole. So move RAX 0, right? 0. Here 0 if it's not a float, and it's not. RDI is the format, address, or string. Now I want to print X. Now is that a string? No, not yet. It's a number. And so what I'll do is first I gotta get a format. And so where do I put my format? I put it in my data. So format. How long is my format? It's usually always DB for strings, and this will hold a number. Okay, end of string. So now back to my thing here. It says in my RDI, put your format. So in my RDI, put my format. Okay, so my format is done. Next step, in my RSI, put what you want to put in there. So now what do I want to put in here? So it's saying in my RSI, in your RSI, which is the first, if you're taking 2 inputs, it would be RSI RDX. And my first input, RSI. So move RSI. What do I want to put in this holder? Remember, I said it here. Takes format placeholder. So whatever I'm putting in the placeholder here. What am I putting? X. Now what is X? X is RDX. So I'm going to put in here RDX. Okay, so that's done. Now that's it, that's done. Now I can call my function. So now what I'll do is I'm gonna use what he uses, which is always push. Then I call printf, and then I pop RBX. All right, and you see now this should print. So the way this would work is this will start. I have my X in RDX, I have my Y in RCX, I have my R8 and Z, I have my Z in R8. Then I'm gonna compare my RDX, which is X. I'm gonna compare 1 to 5. This line says if 1 is less than 5, jump to this section. All right, so this will jump, and it will do this, and then after it's done this, it will print, which is right. Now here, after this, what I can say after, so here, what do I want to say? I want to do the else statement, right? So this says if 1, right? It says if X is less than 5. That's good. Now what if it's not? Then this won't run. This will be skipped, right? This only checks. This will only jump to this section. This will only jump here if this condition is true. Now what if my X was 6? So it's not true. What will happen? Then what I'll do here is I'll be like, okay, then if that's the case, do this. And so what I want to do is add my X plus Z. My X, RDX, plus my Z, which is R8, right? Now, if I leave it as is, like this, what will happen is, obviously I will compare, I will check this. This is 6, that won't run. Therefore, I'm gonna do, my X plus Z, okay? But it will still run this. But I don't want it to run this. I want it only to run this if this condition is met. So what do, I do jump, right? And I believe it's just JM for jump. Where is it? JE. I don't have it included here. Let me grab it real quick. Yeah, so it's actually pretty simple. It's just GMP like I thought. And so, yeah, so now I'm going to jump to print. That's what I did. So now what I did is I'm saying check this statement. If it's true, jump here. If it's not true, add these, and don't play this because then jump print. Then what happens is it will skip this and it'll go straight to print. And that's what I want. This what it says is check this statement. If it's true, do this, right? So if this is true, then this part is right here. But if it's false, just continue. You add RDX plus 8, so do this, and then jump to print, because I don't want to run this. This is not true. Okay. Now, what are labels? Labels are what you want to jump to. So whenever you want to jump to a place in your code and you want to do a loop, you want to do a label and you can jump to it. So you see, if I did this, watch this. If I do a label, if I make a label called while true loop, okay, and if I do jump, while true, okay, if I do this, what will happen? I'll enter while true, and then I'll do this line. This line says what? Jump to while true. So then I go back here, then I come here, jump while true, go back here, come back here while true, jump. And this is the infinite loop, okay? And so that's what labels are. This section is you use them with your labels. So you do whatever you want, comparison, and you jump to whatever label you want, okay? And so that's done. This is how basically you do this. So you see here in his code, he also used RA, okay? He compared, but he did if it's more, so he used a little bit different, but they're both the same. So it depends on the way you think. There's multiple ways of writing this, whatever you're comfortable with, all right? But both ways are right if you want to study both, okay? Now we're gonna go to this while true, and so now let's delete all this. This is our last activity, and then after this, I'm gonna make one more lecture to do the exam review. So convert the following code, C++ code, into assembly. So first we have to declare this. Let's declare section.data, and then I know my x db1, right? And db1 fits into 1 db, so it's fine. All right. Now my next section is text. Here, what I want is optional. First, let's start our code properly. Okay. And now here I want a while true, but the while true is upon a condition, this condition. And so you know what I'm gonna say? I'm gonna say here while. This is a label, right? This is a label, and I'm saying while. Now what is my condition? I'm gonna compare. Before I compare, obviously I cannot compare x. I have to put x in a register. And so what am I gonna use for this register? What did he use up here? RCX. This is for the past example, by the way, but I'm just gonna use this register since we used it last time. Okay, and so that would be RCX. I'm gonna move RCX. I'm gonna put my x into there. And actually, sorry, before we move to this step, I just remembered a step that I forgot in this section. Here, right, this whole code, I moved x into RDX. But here what I'm printing is x, okay? Now the value that after the addition I did, right, after this addition, they told me to equal it to x. But here this addition doesn't equal it to x, it equals it to this register. So don't forget, after you print, at the end of your code, to move x, to move the value that you added back into x. So now this equals the new addition, just like this code says. Okay, so make sure you have this. Okay, and I believe he also did it. Yeah, see, move x, RCX, store x into the data. Okay, and so what this basically does, it takes the value that we added here from the register and puts it back into the RAM. And so now, just so you know this. All right, I couldn't backtrack to I'm gonna have to rewrite this. And the example we're doing is this one. So x db1, and then section.text, and then global start, and then start. All right, and then we had a while. Okay, now here it says compare x less than or equals to 5. And you see, well, I can't use x, it's in my RAM, so I gotta first bring it into a register. So I'm gonna use RDX, and I'm gonna use it as x. All right, was RDX for this example, right? Now we use RCX, so I'll use RCX for this one as well, just to keep consistency. Okay, now after I moved it, it's gonna enter this label. Now I'm into this label, and what I want to do is compare. So compare, and the things I want to compare is RCX and 5, right? Now, if RCX, so while x is less than this, I want it to keep the loop, right? So while RCX is less than this, I want it to keep the loop. Now, how do I accomplish this? You might think, this is what I was talking about earlier. You might think to use JBE. This says A less than B. So if I do this, JBE, this will jump, right? If this is true, let's say this will jump out of the while true. But we'll jump to loop exit. So we'll name this actually instead loop start because it's easier to read. So here the loop starts, it compares, and if x is less than or equal to 5, it exits. And then here we'll have our label, loop exit. Okay, and this is like the end. Let's say this is like a exit syscall, end of program. Okay, and so, but the problem here, watch this, x will always be less than 5. So this loop, as soon as it compares, this will always be true, and it will exit. This loop will not keep going. But here, as you can see, the loop keeps going if x is less than or equals to 5. Here, the loop exits if x is equal or less than to 5. Okay, so you pay attention to the difference. All right, so what I want is I want it to exit if what? So when would this exit? Here, when would this exit? This will exit when x is more than 5, because it will make this statement false. So when x is more than 5, this becomes false, it exits. So I exit when x is more than 5. And therefore, my more than 5, where is it? It's JG. A more than B. And so here is going to be JG. That's when I exit. It's when my x is more than 5. Okay? So now we've accomplished when to exit. I don't need this here. This is just to make a point. Now the next point, they want us to print. So let me print. In order to print, we're going to go back to our print right here. We need RAX to be 0 since this is not a float. And then I need RDI to be the format address. And so let's create a format here. And obviously I'm only holding a number. So that's the format. And it says move that into the RDI. Right? It says RDI is format. So we did. Next step is the number you want to put into this format. The number that goes in here. What number goes in here? That goes into the RSI. So move RSI. What number goes in here? What number? Let's see. X. And so what is X? X is RCX. That's my X. And so since I did this, now it's done. I can call print, but obviously don't forget your push RBX, call printf, and then push pop RBX. All right, now that we did the print, so that now the print section is done, it wants me to increment X. How do you increment X? Let's see, we go down, and where's my increment? There it is. Increment register. We'll do register plus 1. So if I do inc the register, which is, what's my register? RCX. This will increment X by 1. Now pay attention here. We pass the address of X. We're supposed to pass the value of X. Because remember, we're comparing numbers. We don't want to compare address with number. We want to compare number with number. Okay? And so now I incremented it. So this part is done. Okay? Now if I leave this like that, it entered the loop start. Remember, this is just a label. This doesn't actually mean a loop. This is just a label. Now, it will compare. Is X less than 5? Yes. So it's not going to exit because this is this condition. This condition says X more than 5. So this is false. It won't run. So first, it will print my X. And so this will print my X. Then it will increment my X. Now my X is 2. But then now it will go here. I want this to jump back up here. Because remember the loop? After I finish this, I want it to jump back here. And then check, do the comparison again, increment by 1, and jump again until X becomes more than 5. And so what I'll do here, I'll do jump to loop start. And so here, after increment, it will jump to loop start. So it will go back up here. Compare, check if X more than 5. No. Print X, increment X. Now X is 3. Jump back to loop start. Back here. Okay, compare. Is X is 3. Is 3 more than 5? No. Keeps going. Go back. Now it's 4. Is 4 more than 5? No. Okay, goes up, back up here. Now it's 5. It's 5 more than 5. No. So it keeps going. Now it's 6. It's 6 more than 5. Yes. And so if 6 more than 5, we'll go to this label, which is here. So now it skips and it goes here. Now in here, what do I need to do? It says make x equals 0. And so first, what I'll do is move RCX. That's my x. I just want it to be 0. Then I'm going to move x, and I'm going to move RCX into x. Because obviously I want x. This is the register. This is not x. This holds the value of x, but it's not x. And so that does it. Or you can technically also say move x 0. That technically does it too, but this looks a little bit cleaner. All right. And now, if you remember, always we do move rax 60, and we also do move RDX 0. And this here we do syscall, and this is right here. Sys exit rax is 60, RDI is 1, so this is RDI, and not 1. You see, if you remember, this is error code. Usually it's 0. You can put it 1, you can put it 50, you can put 100. That's your call. I put 0, and this ends our program. And that's how you do while loops. If you look at the way he did it, he moved RCX x into RCX, compares, checks if it's more than 5, does the whole print, increments RCX, jumps loop start, and then here it moves RCX 0, then it moves RCX into x, and we have our data is the same, and that's it, guys. This is assembly in a nutshell. Now we do have one more thing, which is functions that I want to talk about. All right, now remember here I have this loop exit, and I call it. Now what if, you know, this print, what if I don't want this print to, you know, take this whole space? What if I want to make a function for this print, right? And so what I'll do here underscore, and I believe you can even not, like, I can name this print like this, or I can name it underscore print. And what I'll say here, I'll tell it what to do. And so what I want it to do is I want it to move rax 0. And I can tell it, you know, move RDI. Basically, I'm going to take this whole thing and I'm going to put it here. Now, do I have to, what if I want to pass variables? So you see how here I passed format as an RDI into my function. This is a function, by the way. So here I'm going to call it. So I'm going to remove this whole thing. I'm going to call it. I'm going to be like call print. Right? Here I call print. So when this runs, I call print. Now what's the difference between call print and jump? Right? When you jump to print, this will do the whole thing, and then it will continue down. Unless I do, you know, jump back to loop start. But then this will go up here, and then it will recall this again. And this will be an infinite loop. So what I'll do is something called a ret. This means return. You know, in Python or C++, you do int, add, you take int a, and then inside here, I'll do a++, and I'll do return a, right? That's it. That's how I do it. Here, that's what return. I'm returning the value. And so this will return the value up here. Now the question is, what register does it return the value into? This actually is a bad example. I'm going to use a better example on this. Actually, you know what? I'm going to delete the whole code. So I'm going to use a simple example that will explain how to use functions. All right. Okay, so now we start, and let's say I want to add 2 variables. So I'm going to do move rax 5, variable 1, and then move, what's my second variable? I'm going to use RDI. Okay. If I go, where is it? Oops. RDI. Let's say I want to add these 2. So I'm supposed to get 10, right? Now if I want to add, instead of here doing add rax and RDI, what I'm going to do is I'm going to make a function that adds these 2. So what I'm going to say is I'm going to say call addition. That's what I'm going to call my function. I'm going to call it addition. So here I'll do addition. All right. So in here, obviously I have to pass it. I have to pass this function these values. Okay, how do I pass them? So you see here, I wrote it for you guys in my functions. So you see these first two, by the way, these first two, these are not functions. These are just, I have a loop start. This is a while loop, and this is an if statement. This is the actual function. And so when you declare a function, you declare the name like this. So whatever the name you put, I'm not saying these brackets are not there. I'm just saying like this is the name. And then you put 2 dots, and so this is how it is. I can also put underscore before or not. That also works. Okay. So now these actually are mostly for global names. So here for labels you can put it or not put it, doesn't make a difference. But it's better practice not to put it for labels, and you only put it for global variables. You put an underscore beforehand. Okay. So anyways, addition, and here we want to do the addition. Now to this function, I gotta pass it these values. Now how do I pass it? If I go here, as you can see in the function, my arguments are RDI, RSI. So these are in order. My first argument is RDI, second argument is RSI, RDX, RCX, R8, R9. And if you need more than 5, so these are what? These are 6. If you need more than 6 arguments, the rest you have to push to the stack. All right? And so let's do this. Let's put X in RDI and put the other in RSI. So instead of having it like this, RDI is 5 and RSI is my second argument. So RSI, let's assume my second, I want to add these two. So my RSI is my second argument, and it's going to be 10. My RAX is going to be 0. Okay, then I'm going to call. I'll explain why this is 0. All right, then I'm going to call. Now, when I call, this will go to this function. And what I want to do here is add RDI and RSI. Right? Everything is so far so good. Then what I'm going to do is return. Then now the code will return to this function where it came from. And here I'll do a syscall. So I'll do a move racks 60. And we say move RDX, I believe. For this section, where is it? Syscall RDI is 0. This is my error code. I use 0. You can use 100. Nobody cares. RDI, and then syscall. So this ends my code, right? Now the way this works is first I move in the rack 0, so I make sure my rack is empty. Then I put my first argument, my second argument, then I call the function. The function will use these as the 2 arguments, and it will add RDI plus RSI and return. Now where does the addition go? We know from our add right here, where is it? We know from our add, it's equals to the A. So is my result in RDI? And the answer is maybe, maybe not. I actually don't know. But what I do know is when a function returns, is it returns the value in the RAX. That's why I made sure it's 0. Because the addition, after I called this here, RAX equals 15. All right? So that's how it works. So here, if I were to call a printf on racks, it'll give me 15. Okay, and that's how functions work. Okay, so I just want to confirm what I said earlier. So here, since we're only changing one of our parameters, your RDI is the one that holds your 15. But usually, when you're writing functions, the way you'll do the addition, you'll do add, you'll do move racks, and then you'll move your RDI into here. Then you'll do add racks, and then you add RSI to it, right? And then you do return. Now this will return to this line, and here my racks is 15. And here what I'll do is I'll do move RDI racks, move racks back into RDI. All right. Now is the other way better? Technically it's shorter, but just so you know, this is the way. If last thing, if you do need more than 6, so if I can find my function, Jesus, if you do need more than 6 arguments and you pass through the stack, then the first argument is at the RSP. And remember, the RSP, if you go to your stack, here stack, my push where is it? RSP. RSP points to the top, grows towards lower addresses, not higher. So your stack, the way it works, this is how it looks like. And this is the high memory, high number memory. And this is like memory 0. Let's say this is memory 100. When you push things to the stack, they don't go from 0 to 1 to 2. They actually go in reverse. So keep that in mind. They go from 100 to 99 to 98. And your top of the stack is actually the 98, not your 100, because it grows in inverse, right? And so if I want to access, so if I go to my code here and I push something to the stack, so let's say here I'm going to do push let's see RDI. Let's say I don't pass RDI like this, and I push RDI to the stack. You see, so this is, right now the stack has 8. So the stack, if I take this, let me draw. This is the last subject, just hang on for a minute. And here, if I have it here, as you can see, the way this would work is, what happened to my mouse? Hello? There it is. All right, so my stack. All right, this is your stack. And this is section 100. This is section 0. And remember, it grows. So inside here, I have instruction. This will go here. Right, that's my first line. Then I have my second line. Then I have my third line. Right, then I have my fourth line. And then they'll call the function. All right, now here, what happens is, when I call the function, it gets obviously added on to the stack. Then it goes here. And let's say I want to access this RDI. You know how I did RDI here? If I want to access this, how can I access this? What I'll do is I will do RPS. I think that's the pointer name. Where is it? Right in, yeah, RSP, sorry. So I do RSP plus A. Now, why do I do this? It's because right now, when I'm at this section, my RSP points to the top of the stack. This is the top of the stack. This holds the call. This is call addition. So if I want to access my RDI, remember, my RDI, I pushed it on here. This is my RDI. Right? And so in here, my RSP points to the top. So this is the RSP points here. Okay? And so if I want to get my RDI, I will do RSP, right? And I will add 8. Now you're going to think, why are you adding 8? Why don't you minus 8? Remember, here, this is, let's say, section 100 minus 8, 92. So this is, well, let's see. This is 100. This is 92. This is what, 84? 6, 2, yeah, 8. That's 84. And then I have 78. Minus 4, no, 76. Okay, so that's number 76. And then here I have 68. Okay, and so RSP now points to 68. RSP equals 68. So if I do RSP plus 8, that's 76. And that's where my RDI is. And so to access it, if I push it on the stack, I will do this. All right, and that's how you can access things in the stack in your function, right? And now I'm going to go back to my page, and I believe that's all I wanted to teach you guys with assembly. Now you know how to do while, you know how to use functions, you know how to do lists. You basically know everything. This is everything you need. I'm pretty sure after this I will do the exam review, and good luck everybody on your stuff.